Okay, welcome back. 11.3, the Binomial Theorem, our last lesson of this unit. Introduction. Let's talk about Pascal's triangle. Examine Pascal's triangle and identify at least 3 patterns. Compare and discuss with a partner. So I'll pause here. If you're working by yourself, think about what patterns you might see. If you're working with someone, think about the observations you might have. So I'll start writing some down here. Pause it here if you want to try before I write them down. Okay. I have rows. This is an observation. As we go up in row, so row 1, row 2, row 3, row 4, row 5, and so on, well, what happens? Observations, outer edges are 1. So 1, 1, 1. Okay. Each row after row 2 is a sum of previous values in row above. Okay, what does that mean? 2 is equal to 1 plus 1. 4 is equal to 1 plus 3. 6 is equal to 3 plus 3. Okay, maybe one more that I can see. If you can think of more, awesome. Okay, last one is row 1 has 1 term. Row 2 has 2 terms. Row 3 has 3 terms, and so on. 4, 5, 6. Okay, so the row number tells you how many terms there are. Write the next 2 rows of the Pascal's triangle shown here. So let me clean this up a bit here. Okay, next 2 rows would look like this. Remember, it's just the sum of the previous values in the row. So the edges are just 1. If you want to think about why the edges are 1, okay, if I have a 0 here, because there's no number, 0 and 1 is still 1. That's why it's still 1. 1 and 4 is 5. 4 and 6 is 10. 10, 5, and 1. Okay, let me just clean this up here, folks, a little bit so I can make some room. Okay, and then the next row, it's just 2 rows. So again, a 0 and a 1 is just 1, 6, 15, 20, 15, 6, and 1. This characteristic of Pascal's triangle will become more apparent as we do more examples and as we explore a topic later in the unit called the Binomial Theorem. Okay, so 1, 5, 10, 10, 5, 1, and 1, 6, 15, 20, 15, 6, and 1. There's your 2 extra rows. Okay, let's talk about the properties of the expansion of x plus y to the n. N is your exponent. The expansion of x plus y to the n, where n is between 0 and 5 inclusive, is shown below. So x plus y to the 1, anything raised to 0 exponent is going to be 1. X plus y to the 1, well, it's just the binomial itself, x plus y. We should be familiar with this binomial expansion, x plus y squared equals x plus y times x plus y. If you remember doing this from grade 10, x squared plus xy plus xy plus y squared, FOIL, remember FOIL, x squared plus 2xy plus y squared, right? We can FOIL it, we can do it this longhand way, but the binomial expansion, the theorem, and then Pascal's triangle gives us a shortcut on how to multiply these binomials using a shortcut instead of doing this brute force method, okay? And this is all through the patterns that you see from Pascal's triangle. Right, use the above expansions to complete the following. There are how many terms per expansion? So if I start here, folks, okay, this I'll call row 1. The n value is equal to 0, and that's always the exponent on the binomial. So the n value is 0, and the number of terms per expansion. So how many terms are in this expansion? There's 1. So if n equals 0, there are n plus 1 terms per expansion. So there's always one more term than the n value. So look at the exponent on the binomial, on the expansion. Look at the exponent, add 1, and that's the number of terms per expansion. That's also the row number. Okay, the sum of the exponents of x and y in each term. So if I just take x and y, so the degree of this term, so 2 plus 3, that equals to 5, well, that ends up equaling n. So the sum of the exponents of x and y in each term is just n. The exponents of x decrease by 1 term by term from n to 0. So if I'm going from 5 to 4 to 3 to 2, every term, the x value exponent goes down by 1. So likewise, the exponents of y does the opposite. It increases by 1, going term for term from 0 to n. So here, the y value is 0, and then 1. Y value is 2. Sorry, the exponent on the y is 2. Exponent 3, exponent 4, exponent 5. The coefficients in each expansion correspond to the n plus 1th row of Pascal's triangle. Okay, so these are the coefficients. The coefficients would be these. So in here, the coefficients 1, 4, 6, 4, and 1. Okay, so the n plus 1th row. So 4, n equals 4. So this is in the 5th row of Pascal's triangle. 1, 2, 3, 4, 5, 5th row. Next page. In the expansion of the binomial x plus y to the n, where n is an element of natural numbers, the coefficient of the terms are identical to the numbers in the n plus 1th row of Pascal's triangle. Okay. N equals 0, n plus 1th term, n plus 1 terms. So there's 1 term, and it's in the first row. N equals 1, n plus 1 terms. There's 2 terms, second row, and so on and so on. You can also determine the coefficients represented in Pascal's triangle using combinations. That's the whole point of talking about this. Later on, when we do the binomial theorem, we'll actually use this table of combinations to help us understand or to help us expand binomials or find the particular terms of binomial expansions. The term 5C2, or a combination of 5 things taken 2 at a time, represents a number of combinations of 5 items taken 2 at a time. So for the expansion x plus y to the 5th, it represents the coefficient of the term containing the x to the 3rd x squared term. Okay, so where is it on this chart? Right here. Okay. It shows the number of selections possible for 3 x's and 2 y's. Okay, so if you arrange 3 x's and 2 y's, there's a total of 10 ways you can arrange them. Okay, so that's what that 5C2 means. Okay, bookmark this for now. We'll come back to why combinations matter in terms of Pascal's triangle let's do a couple examples. I really want to drill down on this whole relationship in Pascal's triangle between the n value, the exponent, what row number, and how many terms. Okay, so we really need to have this down when we are doing this. Okay. Okay. For the binomial expansion x plus y to the fifth, the exponent of the binomial expansion n equals, well, that's 5. There are n plus 1, so 5 plus 1, there are 6 terms. I will use the 6th row of Pascal's triangle. There are 5 terms in an expanded binomial. This corresponds to what? Okay, so separate problem, right? So there are 5 terms in an expanded binomial. This corresponds to row 5. Remember, number of terms equals the row number. For the binomial x plus y to the n being expanded, the exponent n equals, remember the n value is always 1 less than the row number or the number of terms, so n equals 4. Okay, letter C, an expanded binomial corresponding to row 3 of Pascal's triangle has how many terms? Remember, row number equals the number of terms, 3 terms. For the binomial x plus y to the n being expanded, the exponent n equals 2 corresponds to row 3. Okay, so if we want to quickly check row 3, 1, 2, 3, this is row 3. Row 3, how many terms? 1, 2, 3, what's the n value? N equals 2. The exponent on the binomial x plus y to the n is n. This corresponds to the nth row of Pascal's triangle. There are n plus 1 terms in this row of Pascal's triangle. Remember, always add 1 to the n value. That's the row number and how many terms. So there are n plus 1 terms in the binomial expansion of x plus y to the n. Next page, folks. Okay, just a little bit longer to go. We're just going to do, okay, let's do this page. Row number. So let's fill in this handy chart to look at some of the patterns that develop with Pascal's triangle. Row 1, right, row 2, right, let's just fill all this in. So we're going to go all the way down. 13 rows, right? Row sum. So what is the sum of the values in the row? Well, 1 is just 1. 1 plus 1 is 2. 1 plus 2 is 3, and 1 is 4. 1 plus 3 is 4. 4 and 3 is 7. 7 and 1 is 8. 1 and 4 is 5. 5 and 6 is 11. 11 and 4 is 15. 16. Well, what's happening? Looks like the sums are doubling when you go from row to row. So 32. Oh, 10, 20, 30, 32. Yep. And if I just extrapolate here, it's just going to be, the sum's going to double every row number that you change. So 256, 512, 1024, 2048, and 4096. Okay, let's think of a more compact or efficient way of representing these row sums. Okay, sum as a power of 2. Well, what exponent on 2 will give me the sum of 1? Well, 0. What exponent on 2 will get you a row sum of 2? Just 1. Okay, likewise, 2 squared, 2 cubed, and you see the pattern here. Okay, the exponent, n equals 0, n equals 1, n equals 2. So this is the n value, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, what's the n value here? N equals, what's So x plus y, this is the first row, it's 0. X plus y, this is the second row, n equals 1. Okay? This exponent corresponds to that exponent there. The sum is a power of 2. Okay, so a couple of interesting, neat patterns you see in Pascal's triangle. Example 2, expand a plus b to the 7th using Pascal's triangle. The exponent of the binomial expansion n equals 7. There are n plus 1. There are 8 terms. I will use the 8th row of Pascal's triangle. The sum of the coefficients of the expansion is, in the 8th row, 128 or 2 to the 7th. So 128 or 2 to the 7th. Okay? So this exercise, we're just going to take Pascal's triangle. You take the picture of it, right? And then we're going to write out. So you can pick the 7th row. Oh, sorry, the 8th row. So here's the 8th row. We're going to use these coefficients. So let's recopy this. 1, 7, 21, 35, 35, 21, 7, and 1. And then we're going to use those to help us make the binomial expansion. So we're going to expand a plus b to the 7th. Okay, starting with a coefficient of 1, that's 1. And if you remember from a previous Pascal's triangle, remember this pattern, where is it? Right here. Remember this discussion here. The exponents of x decrease by 1 by term from n to 0. And likewise, the exponents of y increase by 1 term by term from 0 to n. So when we expand, it's a to the 7th, b to the 0, plus next coefficient 7, a to the 6th, b to the 1. So the a value exponent goes down by 1, b value exponent goes up by 1, and so on. Take the third coefficient, 21, a to the 5th, b squared, plus 35, a to the 4th, b to the 3rd, plus 35, a to the 3rd, b squared, plus 21, a squared, b, 3, oops, I screwed that up, folks, sorry. This should be, let me back up here, 7, 6, 5, 4, 3, 0, 1, 2, 3, this should be 4, okay? Plus 21, a squared, b to the 5th, plus 7, a, b to the 6th, and then plus 1, a to the 0, b to the 7th. Well, let's clean this up a little bit, right? This b to the 0 is just 1, so I'm going to just write it out. This a to the 0 is 1, and that's your final expansion. Okay, last part here is you try, pause it here, give it a try, come back, check your answer. Expand x plus y to the 6 using Pascal's triangle. The exponent of the binomial expansion is n equals 6. There are n plus 1 or 7 terms. I will use the 7th row of Pascal's triangle. The sum of the coefficients in the expansion of the 7th row, so 7th row here, is 64 or 2 to the 6th. Okay, 7th row, I have 1, 6, 15, 20. Okay, 1, 6, 15, 20, 15, 6, and 1. So those are the terms I will use. Okay, I start with x plus y to the 6th that equals, so the first term is 1 x to the 7th y to the 0 plus 6 x to the 6th y to the 1. Okay, and you get the idea. Use those coefficients and then watch the pattern of what happens to the exponents on the x and y. Oh man, let me back this up. I screwed this up. Sorry folks. My n value. So it should be 1 x to the 6th y to the 0. Wrong n value. Sorry about that. Okay, so 6 x to the 5th y to the 1 plus 15 x to the 4th y to the 2 plus 20 x to the 3rd y to the 3 plus 15 x to the 2 y to the 4th plus 6 x y to the 5th plus 1 x to 0 y to the 6th. Well, y to the 0 is just 1, so I don't need to write that. X to the 0 is just 1. And there's your binomial. Okay, continuing with our investigation of Pascal's triangle. One more page of notes, and this is important for understanding the next topic, which is the binomial theorem. So let's go over stating values of Pascal's triangle using combination form. So here's our example. Consider the expansion of x plus y to the 4th. How many terms are in the expansion of x plus y to the 4th? So let's try to do this without looking at Pascal's triangle. Let's do this in a mathematical algebraic way. So in our binomial expansion, our n value is 4, n equals 4. So we know that n plus 1 equals 4 plus 1. So there are 5 terms, and that is the 5th row. Okay, so let's start to understand these patterns so that when we get to the binomial theorem, it'll be much easier to understand. Okay, letter B. In combination form, for the term, the combination of n things taken 0 at a time, n is the exponent on the binomial expansion, so n equals 4. So 4c0, combination of 4 things taken 0 at a time, is the first term. What does the number 0 refer to? Okay. Evaluate. Let's evaluate this first. 4 factorial over 4 minus 4 factorial 0 factorial. That is 4 factorial over 1 factorial 0 factorial. All of the denominators just 1. Oh, sorry. Oh, let me back up. Oh, so wrong. Sorry about that, folks. This is 4 minus 0 factorial. Sorry. And 0 factorial. So 4 factorial over 4 factorial 0 factorial. So I have 4 factorial over 4 factorial. As we expect, the first term of any row of Pascal's triangle is 1. So that's what we expected, right? So this is the coefficient of first term. What does the number 0 refer to? 0 is the exponent on the y. Okay, letter C. In combination form, show the notation for the coefficient of term 2, term 3, term 4, and term 5. So if term 1 okay, so term 1 we said is 4c0. And then now I'm going to use the abbreviation T sub 2. That's term 2. Well, that's going to be 4c and then 1. Okay, term 3. Term 3 is 4C2. Term 4 is 4C3. Term 5 is 4C4. Okay, write the binomial expansion for x plus y to the fourth using combination form, then simplify. So what do we have here? Okay, so I have 4C0 x to the fourth plus 4C1 x to the third y plus 4C2 x squared y squared plus 4C3 xy cubed plus 4C4 y to the fourth. A couple things to notice. We have x to the fourth, x to the third, x squared, x to the 1, and then x to the 0. Likewise with y, y to the 0, y to the 1, y to the 2, y to the 3, y to the 4. So we see that pattern developing, right? Okay, and then let's simplify all of this. That is 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. So all these combination values, all these values here, you can use your calculator to calculate and then insert them into the binomial expansion. Awesome. Okay. Letter E. Expansion of x plus, use combination form for the expansion of x plus y to the 11th. Using combination form for the expansion of x plus y to the 11th, write the coefficient for the first three terms of the expansion, then evaluate. So the first three terms. Term 1. Okay, first thing is n equals 11. I have 12 terms. Okay, term 1, the coefficient of the first three terms. That is, first term is 11, C0. Okay, and that's 1. Remember, this is your n value. Okay, and then this value always starts with 0 when it's the first term. Second term, 11C1, and that's 11. Third term, 11C2, and that is 55. Determine the coefficient of the 8th term. So the 8th term, t sub 8, okay, what's my combination? Okay, I know my n value is 11, so I'm going to throw 11 in there. Well, what do I put for the r value? Okay, if the first term, r value equals 1, r value equals 0, right? So that r value always lags the term number, right? So if I'm looking at term 8, then the r value here is going to be 7. Okay, and that equals 330. Okay, last one. Determine the coefficient of the last term of the expansion, then evaluate. So the last term, we know that there are 12 terms total, so t sub 12. Okay, how do I write my combination? So I know n value is 11, and the 12th term, the r value always lags the term number, so the 12th term is just 11. So combination of 11 things taken 11 at a time, that's just 1, and that's what we expect for the last term for a coefficient. Okay, we'll pause here, give this a try by yourself, okay? pause the video. I'm going to go ahead and do it, but if you want to try it, pause right here and then come back in a couple minutes. Okay? N equals 14. There are 15 terms, so let's write down a couple key facts. How many terms? Letter A. How many terms are in the expansion x plus y to the 14th? So n equals 14. There are 15 terms. This is the 15th row. Okay, I'm going to challenge you to, don't use Pascal's triangle. Don't use the picture. Try to think of this mentally and try to reason through this mathematically. Okay, letter B. Using combination form for the expansion x plus y to the 14th, write the coefficient of the first three terms. So remember, it's like this, NCR. Okay, so for term 1, my n value is 14. Term 1, we know we always start with that 0. And that's just 1. Term 2, the n value is 14. Term 2, the r value lags by 1. So that's 1. So 14C1, and that's 14. And then term 3, n value is 14. I'm going to put an r value of 2. And I got 91. Determine the sixth term of the expansion, then evaluate. Determine the coefficient of the sixth term. So t sub 6 equals, I know my n value is 14. If it's the sixth term, the r value lags the term number by 1, so it's 5. So combination of 14 things taken 5 at a time, that's 2002. Determine the coefficient of the 11th term of the expansion, then evaluate. So the 11th term, my n value is 14. The r value lags the term number by 1, so r value is 10. So this combination of 14 things taken 10 at a time, that is 1001. Okay, all right, folks, last one. Determine the coefficient of the last term of the expansion, then evaluate. Okay, last term, I said, what is the last term? I need the number. I have 15 terms, so it's term 15. Okay, what's my n value? 14. And then the r value lags the term number by 1. So 15 for the term number, 14 for the r value, and that just equals 1, and that's what we expect for the last term.